Sample of 28 healthy babies has an average birth weight of 6.83 pounds and a standard deviation of 1.53 pounds. Construct a 95% confidence interval for the true average weight for healthy babies. If another study revealed that babies exposed to cocaine prenatally had an average birth weight of 4.92 pounds, does it seem that cocaine might lead to lower than normal birth weights? Okay, so I've underlined the key phrases here, important in the problem. The first thing we want to notice is that it says construct a 95% confidence interval. So we know it's a confidence interval, and we also know that it's for the true average weight. So we know it's a confidence interval to estimate the mean. Whenever we see that, we know we have 4 steps to do the problem. The first step is going to be to list all the data. So step 1, we'll say record the data. So the data in the problem here, the important stuff for a confidence interval about the mean is going to be the n, the sample size. We'll also need a sample mean in every case. And then we're going to need a standard deviation of some sort, so we'll say S equals. And then we're typically given a confidence level, and from the confidence level we often need to figure out alpha, and we can even go a step further and get alpha divided by 2 after that. Okay, so let's start with the n though. What's the n for this problem? So it says a sample of 28 healthy babies. So n is going to be 28 for us in this problem. Then it says has an average birth weight of 6.83 pounds. So the average is 6.83 pounds. And a standard deviation of 1.53. That's 1.53 pounds. And then it says construct a 95% confidence interval. So the confidence level is 0.95. And from there, we can determine that alpha is 5% since the two of these must add up to 100. Now finally, from there, if we want, we can go ahead and say that alpha divided by 2 is going to be half of 5% or 0.025. Okay, so step 1 is done. We've recorded the data for the problem. The next step that's important in a confidence interval, maybe the most important step, is step 2 to get the table value. So find, in this case, I'm going to write down T alpha divided by 2. You may wonder, well, when we're getting the table value here, how do I know that it's T and not Z? Well, it's very simple. We have to go up to the top of step 1 here and identify that our sample size is small. N is only 28. And once we see that N is only 28, we know, gee, that's under 30. If it's under 30, we're going to use the T value, not the Z value. So it's that simple. So whenever you're about to do this problem, pause for a minute, look back at the sample size, say, okay, if it's small, we'll use T. If it's greater than 30 or equal to 30, we'll use Z. But in this case, it's small, it's under 30, so we're going to go ahead and use T. All right, good. So we know we're going to get T. In order to look up a T value, we need a couple of items. We need to know alpha divided by 2. Well, we've done that already. And then we need the degrees of freedom. So what I'm going to do is write down the steps. We're going to look up degrees of freedom 27. Remember, degrees of freedom is just n minus 1. So look up degrees of freedom 27 and alpha divided by 2 equal to 0.025. And that's how we're going to get our T alpha divided by 2 value from the T table. Let's go do that right now then. Okay, so we're looking up 0.025 and degrees of freedom 27. 0.025 is the third column, and let's scroll down until we get the degrees of freedom 27. Okay, so the number is 2.052. 2.052. Okay, so we found the critical T value to be 2.052. All right, so our next step in the problem then is step 3 to get the margin of error. So step 3 is equal to the margin of error, and that'll be, in this case, since it's a T problem, we'll have T alpha divided by 2, S divided by the square root of n. Okay, so that's the margin of error formula. Let's plug in the numbers now that we've calculated all these values above. The T alpha divided by 2 is 2.052. The S is 1.53. And we're dividing by the square root of n, in that case the square root of 28. All right, let's use our calculator now to calculate the margin of error. 2.052 times 1.53 divided by the square root of 28. All right, so we get the answer 0.5933 dot dot dot. I'm going to store that in my calculator for use later, but of course you can just round off to maybe 4 or 5 decimal places so that you're not committing too much of a rounding error before the final step. All right, the last and final step, the fourth and final step, is going to be to calculate the following interval: x bar minus the error, x bar plus the error. So it's a simple arithmetic problem. We have the x bar, we have the error, so we just plug those numbers in. In that case, we're going to have 6.83 minus 0.5933, let's say, and then 6.83 plus 0.5933. And when you do that, you get 6.83 minus, I'm using the full value in my calculator, and then 6.83 plus that same error. And you end up with the interval 6.24 pounds to 7.42 pounds. Okay, so that's your interval. Let's go ahead and write out the classic statement that we always use when working with these problems. So we'll write out the statement: we are 95% confident that the true average weight for healthy babies is between, and we'll put our numbers, 6.24 pounds and 7.42 pounds. Okay, now let's use that statement and our result here, our interval, to answer the last question in the problem, which says, if another study revealed that babies exposed to cocaine prenatally had average birth weights of 4.92 pounds, does it seem that cocaine might lead to lower than normal birth weights? Well, look, this is where we believe the average weight is for healthy babies, right? We would think it's between 6.24 pounds, 7.42 pounds. 4.92 pounds is lower than that. And that would mean that that's unusually low, and we would say that at this point it looks like cocaine does in fact contribute to lower than normal birth weights, since that number is outside of our interval and it's on the lower end.